Example 22. Determine the magnitude and location of the equivalent resultant force acting on the shaft in the figure. So of course, we have a varying load, not uniformly varying, but just varying load, which is represented by the equation W is equal to 60x squared, which has a unit of force of Newton meter, meaning a force over that entire length. So we are tasked to find for the magnitude and location with respect, or let's say measured from O. So we already know based on the video on force system resultant, reduction of distributed loading, that our resultant force, the magnitude of our resultant force is equal to the area. But of course, provided that our area is represented by uh, a uniform load, but for here in our example, it is varying. It is represented by an equation. So what we're going to do is that we're going to take a strip, right? In our integral calculus, we take a small strip here, which has a length of dx, and the height would be the weight, which is our w, to find in order for us to find for our differential area. So F sub r, if we do summation of our forces, since all of our forces is going down, so summation of forces y is equal to our resultant force. So F sub r is equal to the integral of our differential area, right? Of course, over that entire area. And our area is equivalent to W of x, where it's just our weight as a function of x, dx, wherein our x is the entire length. Okay, so we substitute our W, which is 60x squared. This is equal to integral of 60x squared dx. And of course, we are going to do a definite integration because we want to find for the exact value of our resultant force. So therefore, we are going to integrate 60x squared dx from 0, which is our initial x, to 2 meters. Okay, so this becomes an integral of 60x squared is 6, this becomes 60 times 0 to 2 of x squared dx. And then this becomes 60 times x cubed over 3. And evaluate our x from 0 to 2. This becomes 60 times 2 cubed over 3 minus 0 cubed over 3, right? And this becomes now is equal to 60 times 0 cube is 0, 0 over 3 is 0, 2 cube is 8, so this becomes 8 over 3. And if we multiply 60 times 8 divided by 3, that is equal to, so therefore our F sub r is equal to 160 Newton, and of course it is going down. This is our magnitude of our resultant force. Now for its location, so since we are using integration, we will be, let me label this one as our magnitude. Magnitude. Okay, and for our direction, Direction. No, yeah. Meaning, not really, no, sorry, not the direction, but it is the location. Okay, location. I got used to saying direction for our resultant force, right? So location. So if you can observe our formula, if we do integration, is bar x is equal to the integral of x dA over the integral of dA, right? And we know that dA, x times w dx over w dx. And we substitute our value. Now we know what w dx, right? Because we have calculated it to find for our resultant, that is 160 Newton. So we can immediately substitute 160 Newton here. Okay, this is equal to over 160 and the integral of x times 60x squared dx. X squared dx. Okay, so we bring out our constant in our numerator. So this becomes 60 times the integral of x cubed dx. And we are going to evaluate this one from 0 to 2 again. 0 to 2 divided by 160, which is the value of our resultant. So this becomes 60 over 160 times x to the fourth over 4. Evaluate it from 0 to 2. So this is equal to 60 over 160 times 2 to the fourth over 4 minus 0 fourth over 4, right? And this is equal to 60 over 160 times 2 to the fourth is 16 divided by 4, that's 4. 4 minus 0 is 4. And then, so therefore, our bar x is equal to 60 divided by 60 is 0.375 times 4, that's 1.5. 1.5 meters from O. Okay. So if we try to redraw this one, this is our shaft, our loading, right? We have our resultant force, F sub R. It acts at the centroid, of course. And then this is O. And then this is X. Okay.